Okay, good morning.
Good morning.
We are Spacecraft Detail Design. We'd like to thank everybody for coming in today. We have a somewhat lengthy presentation, a little bit over an hour. And this year, this is our project. We had a lot of lessons learned, which we'll be talking about during the presentation. Students did very well, very proud of them. As you can see, there's a lot of props in addition to the system. And after the presentation, we'll be outside in the atrium if you have any questions after the presentation. I'd like to thank our panelists who took the time off from their busy schedules to come in and panel for us. And you can introduce yourselves.
My name is Kyle Little, and I graduated from Embry-Riddle in 2004. And then I spent some time in the Air Force and worked for Lockheed Martin for a while, and then did some flight control systems. And currently I'm working on SGSS, which is the Space Network Ground Segment Sustainment and Upgrade for NASA, down at General Dynamics in Scottsdale.
My name is Dr. Oleg Cindy. I graduated the same semester as Julio, so I already have the inside man, so I know everything. And I currently work at NASA Jet Propulsion Laboratory. I work on anything from CubeSats to space station instruments, deep space robotic missions, and human spaceflight vehicles. I see the entire spectrum of missions, and I'm really looking forward to your presentation.
My name is Ashley Almond. I graduated in 2013. I currently work down in Houston at Oceaneering Space Systems on the one EVA contract for NASA, sustaining and designing EVA hardware for the space station.
My name is Jacob Alder. I graduated from here in 2012. I've spent the last 3 years in industry doing rapid prototyping and concept development.
My name is Scott Blue. I'm retired Air Force and currently a consultant, and I have spent my entire career, about 38 years, working classified military space programs.
Hi, my name is Jody Davis. I graduated in 2003 and I'm at NASA Goddard Space Flight Center in the DC area working in hardware integration and test for the James Webb Space Telescope.
Again, we'd like to thank everybody for coming in today. And this time, I'll pass it over to Michelle Machado, our project manager.
Good morning, ladies and gentlemen. We're the Phoenix Aerospace Launch Systems. My name is Michelle Machado. I'm the project manager, and this is our system validation review for our project legacy. And over here this morning, we'll be talking about the project introduction, the requirements and experimental validation status of the following subsystems, and the overall system, the configuration management, and management. The goal of our project is to provide a viable launch system that could potentially replace the current high-altitude launch system at the Embry-Riddle Aeronautical University Test Campus for the Experimental Space Systems class. Our alternative launch system is a high-powered rocket called Legacy. Here you can see a format of how we've divided our team up. As you can see at the top, myself, the project manager. At the bottom, the assistant project manager and lead integrator is David Gomez-Herrera. And we broke it down our subsystems into these following 4 categories: launchpad, structures, payload electronics, and recovery. Communicating between these subsystems are 3 integrators. So now I'll be giving you an overview of these subsystems that we have had. As you can see here, and the catalog here with the guide wires is our launch pad. The purpose is to ensure that Legacy is launched within the 5 degrees of the vertical. The structure subsystem consists of the nose cone fins, the rocket body, which consists of 2 parts, the lower structure, which encases the motor, and the upper structure that holds the recovery, electronics bay, and payload subsystem. The payload electronics subsystem has 2 parts to it. The payload section has 6 payloads collecting scientific data as Legacy descends back to Earth, and the electronics bay is responsible for ejecting the recovery system and to ensure that we can track the rocket after the mission has ended. The recovery subsystem is responsible for ejecting the nose cone and allowing Legacy to return back to Earth with the payloads using a parachute. The project is broken down to these following mission objectives. Legacy should reach an apoapsis greater than 9,000 meters, but less than 13,000 meters. It should transport 6 scientific payloads. The total of mass of the scientific payload should be less than 10 kilograms. Legacy should be reusable for more than one flight. It should return to Earth using a parachute and using a commercially available motor. The motor that we've designed for is a Cesaroni O3400 motor. Here you can see a concept operations for our flight. At 0 seconds, Legacy will launch. At 6.32 seconds, the motor will burn out. At 34 seconds, the nose cone will eject. At 39 seconds, Legacy will reach its apoapsis, and at this time, the opening force of the parachute will pull out the scientific payloads and start to make its descent, as you can see here. Approximately after 25 minutes after reaching apoapsis, Legacy will have its projected landing time. We've encountered some issues this semester, as noted by Dr. Benavides. First of all, we were not able to launch our rocket last Saturday in Aguilar, Arizona due to some issues. First of all, we had issues with communication between the prefects in the beginning of the semester. When we actually got down to Aguila at the launch site, we were told that our goal, the design of our mission, maximizing the time that we have in the air was not allowed because we would be potentially we'd be exceeding our radius limit. And also, because of that, we were not able to launch Aguila. We were not able to find a feasible launch site with the time that we were given. And also, when we ordered the motor casing during spring break, unfortunately, 2 weeks later after we ordered it, the vendor notified us that the factory caught on fire and delayed shipping for the motor casing. And so it actually, unfortunately, came in on Tuesday, as you can see here. The team leads for the subsystems are as follows: Wesley Goldner Carver for Launchpad, Isaac Perry Structures, Jonathan Winters Payload Electronics, Jose Cria Recovery, and David Gomez Herrera for Integration. And now I'd like to pass on to Wesley Goldner Carver, who will be discussing the Launchpad subsystem test.
Thank you, Michelle. As my colleague said, my name is Wesley Goldner Carver, and I will be discussing an overview of the Launchpad subsystem and a couple of tests we ran to validate our requirements. So I'm the team lead of the Launchpad subsystem, and working with me are Neil Noonan and Jared Wong. So Michelle discussed the purpose of the Launchpad, so here are some objectives from it. We would like to safely launch Legacy and do so multiple times. It can be easily transportable. The Launchpad structure you can see right here is completely disassemblable to make transportation easier. We also have adjustable rails. This allows for multiple rocket diameters. So, and again, here's a visual overview. This just has some call-outs to the main components of the Launchpad. So we have a base, a guide rail, so this consists of the aluminum C channels and the square aluminum tubes that are up against the rocket. A stiffener section. Purpose of this is to keep the C channel rods from flexing. We also have guide wires and ground stakes, which are these two things right here. Now, the purpose of these is for an actual launch scenario to apply restorative force to the launch pad to keep the rocket launching as close to vertical as possible. So some design requirements that we generated off of our objectives. The launch pad shall withstand more than one launch. The launch pad shall support a force of less than 890 newtons from Legacy. The launch pad shall accommodate a rocket diameter that is greater than 7.62 centimeters, and it should also accommodate a rocket diameter that is less than 15.24 centimeters. The launch pad shall withstand a wind velocity that is less than 20 miles per hour, and the launch pad shall launch the rocket within 5 degrees of vertical. So here are the performance metrics we use to validate our launch pad. For withstanding more than one launch, the metric we analyzed was the structural integrity. Our numerical analysis to validate this requirement was done through ANSYS, and our experimental analysis for this requirement was done through our certification of materials testing and our rocket forces test. All of our experimental tests we will be going into detail. To accommodate the rocket diameter between 7.62 and 15.24 centimeters, the metric we analyzed was the diameter of the rocket. Our numerical analysis was done through CATIA, making sure the model of the rocket could fit inside the launch pad model, just making sure it fit properly. And then the experimental analysis was done by physically putting the rocket structure inside the launch pad and making sure it fit properly. To validate withstanding a force of 890 newtons, the metric we analyzed was the applied force, and this is from the weight of the rocket as well as the exhaust gases on launch. This numerical analysis was done through ANSYS, and the experimental analysis was done through our rock forces test to ensure that, I'm sorry, I apologize for that, to withstand a wind velocity that is less than 20 miles per hour. The metric we analyzed was the deflection of the rocket, deflection of the sea channels. And this was done, our numerical analysis was done through ANSYS, and our experimental analysis was done through our wind loading test. To validate the requirement of launching within 5 degrees of the vertical, again, this was, the metric we analyzed was deflection in the sea channels, specifically the tips of the sea channels. This was numerically validated through ANSYS, and experimentally that validated through our wind loading test and our locking out test. Now we'll be discussing how we conducted our certification of materials testing, as well as the results from this testing. The purpose of this test, these tests were to validate that the launch pad could withstand more than one launch. We did tension and compression testing with the materials of our launch pad. This is 6061 aluminum and A36 steel. The figure on the right just shows a tension specimen, aluminum sea channel tension specimen being tested in our United load frame. A point of note right now that I have to say, we could not perform our tension testing, or excuse me, compression testing due to the capabilities of our facilities. So here are the results of our certification tests. In the second column, you will see the published yield stress values from Military Handbook 5, which we were comparing our experimental analysis to. In the next column, you'll see our experimental results, and these are just for the tension. Specimens. The next one will be our numerical values. Now, these were generated from our ANSYS models, and the last one is our acceptance factor of safety. So, as you can see, we have high factors of safety compared to our analytical analysis to our experimental analysis. Though we could not perform the compression testing, it is known that the compressive yield stress values are similar to the tensile yield stress values. So we feel that with our high factors of safety that the requirement of withstanding more than one launch is validated. Now I'll be discussing how we conducted our wind loading testing and the results from these tests. So the purpose of this test was to validate that the launch pad could withstand a 20-mile-per-hour wind, as well as validate that it could launch the rocket within 5 degrees of vertical. As I mentioned earlier, the metric we were analyzing was deflection in the tip of the sea channel, and this was done by using a measuring tape. Technician got up on a ladder and just measured the deflection as we applied the load to the structure. Now, it is hard to apply a pressure loading to a 10-foot structure, so we did a point loading force at the center of pressure of the launch pad, which is about approximately 5 feet. The way we did this is shown in the figure on the right. We wrapped a steel wire around 3 of the guide rails and pulled it into tension using a mechanical winch. Now, the maximum force we applied was 33 pounds. This comes from the point force of a 30-mile-per-hour wind, and the reason we use a 30-mile-per-hour wind is a factor of safety on top of our requirement for 20. These pictures on this slide just show how we conducted the test. We used a load cell attached from the mechanical winch to the wire we were pulling in tension, and this is how we were able to tell how much load we were applying. This was connected to a power source and a multimeter, and we read the voltages and then converted it using the sensitivity on the data sheet. The picture on the right shows our mechanical winch setup, set up on a platform with various clamps. Now, the purpose of this was to put the mechanical winch at the 5 feet at the same height as the center of pressure, so we were not applying a angled load to it, which would throw off our analysis. Here are our numerical and experimental results for our wind loading test. Our numerical results from ANSYS, our deflection shows that we're at 0.414 centimeters, and this is the highest deflection, and this occurred in the tips of the sea channels. But the tip deflection required to get to at least 5 degrees of deflection, which would thus not validate our requirement, was 26.7 centimeters. So from now onto our experimental analysis. The experimental analysis, or experimental deflection we found was 4.45 centimeters. As you can see, this is an order of magnitude larger than our analytical analysis. The reason for this is because we were conducting our wind loading test inside of the structures lab, where unlike our analytical analysis that had a model for the guide wires, we were not able to attach them to the cement floor, so there was going to be more deflection in the sea channels. So this test failed based on our criteria, but it passed in validating the launching the rocket within 5 degrees of the vertical because there was only 4.45 centimeters of deflection compared to the necessary 26.7 centimeters it would be required to get out of the 5 degrees. So another point of how we validated our withstanding the 20 mile per hour load, 20 mile per hour wind, we saw through our test no plastic deformation in the structure, and under the requirement of withstanding the 20 mile per hour loading, or 20 mile per hour wind velocity, excuse me, we feel that because of no plastic deformation, this requirement is validated. Now I'd like to invite up Neil Noonan to continue discussing the launch pad.
Thank you, Wes. As my colleague mentioned, my name is Neil Noonan, and I will continue talking about the test that we used to experimentally validate the launch pad. The next test we'll talk about is the rocket forces test. This was to make sure that the launch pad could withstand the forces due to the weight of the rocket and the exhaust gases when the motor is fired. We determined that this, with safety factors, would be a max loading of 890 newtons, and we applied that through the weights seen in this picture. Now, we collected we collected strain data and deflection data. And you can see where we got this data. We applied the dial gauge, seen here in this picture, to the maximum deflection we expected from our numerical analysis using ANSYS. And we did the same with the strain gauges. And this was located on the cross piece brackets. And the cross piece is this piece in the middle that holds up the rocket when it's being prepared to fire. And this was at the location of max stress and strain we got from our numerical analysis. Now, you can see in this table the summary of our results. In our numerical results, we had a deflection of 0.007 centimeters, a stress of 50.3 megapascals, and an expected strain of 250 microstrain. Now, in our experimental results, we had almost an order of magnitude larger deflection than we expected at 0.066 centimeters. The reason for this is that in our analytical results, we applied we had this stiffener section here constrained, which it would be in a launch condition with our guide wires. And in their experimental results, we actually couldn't add those wires into the lab. There's no way to pound the stakes in. So that's why there's much a larger deflection. Now this is still okay because we want to make sure that the deflection would not cause any problems keeping the rocket from leaving the launch pad. And this deflection is much smaller than a 0.63 centimeter gap we left between each guide rail seen here and the rocket. Now we got the stress of 44 megapascals from using Hooke's equation from our measured strains of 220 microstrain. This strain is less than the strain we expected from our model. And the reason for this is that in our model, we applied a point force in the center of the cross section to represent those applied forces. In reality, the forces are going to act over a distributed area pretty much equal to the diameter of the rocket. And we actually did achieve this in our experiment, so we do believe the experimental results are more accurate than our analytical results. Through these experimental results, we do feel that we validated the requirement that the launch pad withstand the 890 Newton force from the rocket. The next test we'll talk about is the locking knob test. The reason for this test was to make sure that any forces the rocket produced normal to the guide rail would make sure that they could resist that force and not allow the rocket to leave at an angle greater than 5 degrees. We determined that the max load we could expect to see would be 312 newtons, and we measured deflections using dial gauges in this setup seen here. We have the dial gauges, we have the guide rails supported by 2 tables, and then a applied load equal to that 312 newtons incrementally applied on the middle. And we collected those deflections or displacements using the dial gauges. Now here you can see our results. We knew that if we saw the guide rail seen here slide through the back of the C channel more than 3.68 centimeters, we would the rocket would be able to leave at greater than 5 degrees from the vertical. And so we want to make sure we didn't get that number. And in our experimental results, we actually saw a much smaller deflection of 0.062 centimeters. And we don't actually believe that's due to any slip of the C channel through or the guide rail through the C channel, but rather due to the way we conducted the test. It was closer to a 3-point bending test with the tables as supports, and that applied load is that third point, and thus that's more likely due to the deflection of the C channel. Regardless, this the deflection or displacement is much smaller than that required to cause the rocket to leave at greater than 5 degrees from the vertical. Thus, we feel that the requirement is validated. In this table, you can see each requirement and the test that we used to experimentally validate them. We did experimentally validate each requirement. Thus, we feel confident that the system would be able to launch the launch legacy successfully. In future improvements, we would like to put the launch pad into a wind tunnel and get that wind distributed loading over the entire launch pad versus that point load that was an approximation. We'd also like to perform the experiments using the guide wires. This would be so that we could see the results closer to the actual launch conditions, despite the fact we have experimentally validated every requirement. We'd also like to perform the material test to the expected analytical stresses. This is due to the fact that while our facilities couldn't test those materials to their failure, we could apply those loads to the stresses we expect and see what deformation we might have and further validate our system. We'd also like to make better test specimens. We saw that some of them failed in the grip section, and they may have had strain hardening due to cutting with the bandsaw or some heat treatment due to sanding with the belt sander, and thus we want to make sure that those specimens are as the best we can make them. We'd also like to perform tests to see how the launch pad would handle the high corrosion environment of the launch setting. Now I'd like to invite Isaac Perry up to talk about the structure subsystem.
Thank you, Neil. As my colleague mentioned, my name is Isaac Perry, and I'll be discussing the tests and analysis for the structure subsystem. Also presenting with me today are Akash Joseph and Darren Wong. Here you can see some concept art for the design of the structure for Legacy. At the top, we have the nose cone, which is designed to withstand the dynamic pressure expected to be encountered during the mission. Then we have the upper structure, which is designed to accommodate the scientific payloads along with the electronics and recovery subsystem. Below that, we have the lower structure, which will accommodate the solid rocket motor. There are 4 fins located at the base of the structure, as you can see here, which will assist in stabilizing Legacy during flight. There are 3 bulkheads located at the base of the structure, at the top of the solid rocket motor, and directly below the scientific payloads. There are 5 centering rings located at increments of 8 inches from the base of the structure, which will assist in stabilizing the solid rocket motor. And there's a base plate located at the base of the structure, which will protect the interior of the structure from the thermal environment of the solid rocket motor. Our system level, the requirements for the structure subsystem are that the structure shall transport 6 scientific payloads. The structure shall accommodate the solid rocket motor, and the structure shall survive more than 1 flight. The system level requirement for the structure is that the apoapsis of Legacy from the launch pad shall reach greater than 9,000 meters. Here you can see a table showing our requirements and the tests that were used to validate those requirements. Here you can see a continuation of our requirements and the tests used to validate those requirements. Due to our limited time, we will not be discussing all of these tests in this presentation. However, we are fully prepared to discuss any of the tests during the questions and answers session afterwards. Here you can see the design metrics that were analyzed in our tests, and the software that was used to analyze them, including ANSYS, OpenRocket, and Microsoft Excel. And here you have our performance analysis methods, which included using a united load frame to determine the material properties of the materials used in the structure, thermocouple, which was used to ensure that the structure would be able to withstand the thermal environment of the mission. Direct loading refers to weights that were applied to the structure in order to determine and be able to withstand the forces expected to be encountered during the mission. And a digital scale, which was used to measure the densities and masses of different parts of the structure. Here you can see our ANSYS result for thermal analysis. The maximum temperature occurred at the tip of the nose cone and was equal to 578 degrees Fahrenheit. A heat gun test was performed on the nose cone to verify that it would not significantly weaken or deform when temperature was applied. Here you can see the nose cone with a thermocouple, which was attached to it using a piece of silicone tape, the heat gun that was used in the test, and the thermometer that was used to record the temperature. The pass-fail criteria for this test was that if the yield temperature exceeds 306 degrees Fahrenheit, then the test shall be considered to validate the requirement. The reason this is different from 578 degrees Fahrenheit is because this is the average expected temperature during the acceleration portion of the flight. Here you can see a closer-up picture of the thermocouple and a picture of the interior of the nose cone after the test has been conducted. And as you can see, there's been no damage to the structure and therefore it was considered to validate the requirement. The purpose of the medium density fiberboard firmness test is to verify that the medium density fiberboard centering rings used inside the motor section of Legacy would be able to withstand the forces expected to be encountered during the mission and not shear apart from the skin in the motor section. The test was conducted by taking a 65-pound weight and placing it on top of one of the medium density fiberboard centering rings and verifying that it did not shear apart from the skin. And this test was conducted and the requirement was validated. The purpose of the bulkhead C compression test was to verify that bulkhead C, which is located in the payload section, would be able to withstand the forces expected to be encountered during the mission from the scientific payloads along with the electronics and recovery subsystem. The test was conducted by taking a barbell and placing it inside of the payload section of the structure on top of bulkhead C and loading it up to 200 pounds. The pass-fail criteria is that if there's no plastic deformation or visible cracks, then the requirement shall be considered validated, and this test was conducted and the requirement was validated. The purpose of the bulkhead rib compression test is to verify that the bulkhead ribs used in bulkhead A and B would not fail in compression during the mission. The test was conducted by taking test specimens identical to the ribs found in bulkheads A and B and inserting them into a united load frame and applying the load and compression until the test specimens fail. The pass-fail criteria is that the ultimate compressive stress of the ribs is bound to exceed 1 KSI, then the requirement shall be considered validated. Here you can see the data that was gathered during the test and the numerical result for the compressive stress that is expected to be encountered in the ribs during the mission, and the experimental result, which as you can see exceeds 1 KSI and therefore the requirement is considered to be validated. The purpose of the full structure mass test is to verify that the full mass of the structure would not exceed that for which Legacy is able to reach an apoapsis of 9,000 meters above the launch pad. The test was conducted by taking the fully assembled structure and placing it on top of a digital scale and recording the result. The pass-fail criteria was that the total mass is less than 4.5 kilograms, then the requirement shall be considered validated. Here you can see the numerical results for the estimations of the mass of the structure. And the experimental result, which as you can see is 3.15 kilograms, which is less than 4.5 kilograms and was therefore considered to validate the requirement. And with that, I'd like to pass it off to Jaron Wong, who will be discussing more tests and analysis.
Thank you, Isaac. As my colleague mentioned, my name is Jaron Wong, and I'll be continuing with the structure subsystems test and results. Here we have the aluminum spar and ring compression test. The purpose of this test is to verify that the aluminum spars and rings will not break or weaken significantly after the rolling process. Here we can see an aluminum specimen loaded into the united load frame in the materials lab in AXPAT between two compression plates, where a downward compressive force was applied to the specimen until the specimen failed in buckling. Here we have the results from the aluminum compression test, and it was shown that the maximum load experienced during this test was 65.5 pounds, which does exceed the criteria for the test of exceeding 63.8 pounds, which does verify or validate the requirement, Here we have the rivet pull-out test. The purpose of this test is to verify that the rivets will not fall out of the rocket structure during flight. Here we have an aluminum and fiberglass specimen, which is riveted to an aluminum strip where a 45-pound plate was hung. This test was conducted for a duration of 2 minutes, and upon investigation, there were no signs of plastic deformation or visible cracks, therefore validating the requirement. Here we have the rivet drill-out test. The purpose of this test is to verify that the rivets can be removed should the fins, located at the bottom of the structure, need to be replaced after a mission. This test was conducted by taking an aluminum specimen, using a number 41 drill bit, and inserting a rivet using a rivet gun, and removing said rivet with a number 42 drill bit. It is important to note that this test could only be conducted once due to the number 42 drill bit increasing the hole diameter, thus allowing the rivet to rotate. However, it was shown that the rivet could be removed should the fins need to be replaced, therefore validating the requirement. Next, we have the composite compression test. The purpose of this test is to verify that the composites used in the nose cone, the payload section skin, and in the bulkheads do not fail in compression under mission conditions or during flight. Here we have an example of a carbon fiber compression specimen, and this was also loaded into the United load frame, and compressive force was applied. It was shown that the maximum load experienced during this test was 2,080 pounds, which, as you can see in the table below, does pass the criteria of exceeding our numerical results by a factor of 1.5, or in this case, greater than 1.5, thus validating the requirement. And here we have the fiberglass compression test results. It was shown that the maximum applied load was 5,254 pounds, which again, is similar to the carbon fiber test, does pass the criteria of exceeding the numerical results by a factor greater than 1.5, thus validating the requirement. And now I would like to pass it out to Akash Joseph to continue with the structure subsystem test and results.
Thank you, Jaron. As my colleague mentioned, my name is Akash Joseph, and I'll continue to talk about the structure subsystem results and analysis. Here we have the composite tension test. The purpose of this test is to ensure that the composites used for the structure of legacy can withstand the loading during flight. Here you can see an example for the carbon fiber tension test specimen. Here we have the results for the carbon fiber tension test, and as you can see, the carbon fiber test specimen is loaded into the United load frame, and the tension test is being performed. And here you can see a plot for the force versus deformation, where the maximum loading before failure is about 1,074 pounds. The pass-fail criteria for this is that if the experimental result exceeds the numerical result by factor safety 1.5, then the test is considered validated. And as you can see, the experimental result does exceed the numerical result by factor safety 1.5. Similarly, we have the fiberglass tension test result. Here you can see a plot for the force versus deformation, where the maximum force loading before failure is 913 pounds approximately. And we have a similar pass-fail criteria, and the experimental result does exceed the numerical result by factor 1.5, thereby validating the test and the requirement. Next, we have the motor casing accommodation test. The purpose of this test is to ensure that the motor casing can be fully accommodated into the lower part of the structure. And this was done analytically using open rocket CATIA, where the external diameter of the motor casing was equal to the internal diameter of the centering rings, which is found inside the lower section of the structure, and hence the requirement is validated. Next, we have the payload accommodation test, and for this, the purpose is that the 6 scientific payloads can be fit securely into the upper structure, and this was validated both analytically and experimentally. For the numerical analysis, we used open rocket and CATIA, where the external diameter of the payloads was equal to the internal diameter of the payload section. And for experimental testing, we simply inserted the 6 scientific payloads into the payload section, thereby securing it and validating the test and the requirement. Next, we have a full structure shake test. The purpose of this test is to ensure that all the components within the structure subsystem are securely attached and they stay in place. And this was done by simply manually shaking the entire structure, and it validated the requirement and the test. Next, we have the MDF shear test. Purpose of this test is to ensure that the medium density fiberboard ribs used in bulkhead 3, which is found in the middle section of the structure, can withstand the shear loading which is experienced during flight. Here you can see the test specimen inserted into the united load frame undergoing the shear test. Here we have a plot for the force versus deformation, where it shows the maximum loading before failure at about 800 pounds. And we have a similar Pascal criteria to that of the carbon fiber and the fiberglass tension and compression tests, where the experimental result is greater than that of the numerical result, thereby validating the test under requirement. Finally, we have the drop test. The purpose of this test is to ensure that the impact force of the while experienced during landing can be the structure can withstand the impact force upon landing, and this was validated by dropping the structure from a height of 4 feet and 6 inches. And after the test was performed, it was noticed that there was no visual deformations or cracks. In conclusion, here we have a table with all the requirements listed, and as you can see, all requirements have been validated either experimentally or numerically, except for the solid rocket motor accommodation test, which was not validated experimentally because during fabrication for the carbon fiber, there were dissimilarities between the entire section of the carbon fiber, which led to the centering rings from being misaligned, thereby not allowing the motor casing to be slid in perfectly. Next, we have the future improvements. We would like to make some design and fabrication changes by using a standard milling tube as a member for the composite fabrication, as we use a custom size, and this leads to more time for fabrication. And we would also like to use a metal tip for the nose cone and a full fiberglass body instead of using the carbon fiber. Further analysis, we would like to perform vibrational analysis using ANSYS, as well as some wind tunnel testing to improve the design for the nose cone and the fins. With that, I'd like to pass it off to Jonathan Winters, who will talk about the cables and electronic subsystem.
Thank you, Josh. As my colleague mentioned, I am the team lead for the payload and electronic subsystem. I'll be talking about a visual overview of our subsystem and the first set of our tests. The other members of this team are Clark Anderson, Miles Howard, Austin Leonard, and Christopher Ricardo. The payload electronic subsystem is divided into two main sections, which are the electronics bay, which is this, with the main purpose of gathering GPS data and sending it to a ground station to track the rocket, and sending a signal to deploy the recovery subsystem at apoapsis and near apoapsis. The other part of the subsystem is 6 different scientific payloads with the purpose of being used in experimental space systems to gather scientific data. Here is a concept art of the subsystem after it has left the rocket post-apoapsis. The electronics bay and the 6 scientific payloads are attached to a shock cord, as shown here, with the parachute on one side of the shock cord and the rest of the rocket structure on the other side. Next, we'll go over a couple of our main devices. The TI Launchpad is our main microcontroller with the purpose of storing measured data, sending position data to the transceiver, and sending primary control signals to the recovery subsystem. Next, we have the sensor booster pack, which is our primary sensor array. It includes an inertial measurement unit with accelerometers and gyroscopes, as well as a pressure sensor and a temperature sensor. Next, we have a 5-volt regulator. Our payloads are powered by a 9-volt battery, and the TI Launchpad requires 5 volts, so this is used to step down that voltage to power the Launchpad. And this is included in the electronics bay and all 6 payloads, as the electronics bay and all 6 payloads have that Launchpad. Next, we have a 3.3-volt regulator. This is required to step down that voltage for the SD card breakout boards that will be shown later, as well as some of our other sensors, as well as the GPS and the radio. Next, we have a P-channel MOSFET circuit. This is used as a high current switch to allow us to send a signal to the recovery subsystem. Next, we have the egg timer port. This is our redundant flight computer to send a second signal to the recovery subsystem in case the first one fails. This is the NEO MIDM GPS, which is our primary tracking device, and the 3DR radio, which is the way in which we communicate this GPS signal to the ground station. Next, we have the SD card breakout board, which is used to store data to the SD card from the microcontroller. Each payload has a slightly different sensor arrangement, being that each one of them has an additional sensor, a sensor additional to the sensor. The first one has a sun sensor array. Then we have 2 with a digital mini spy pen camera. One will be programmed to record still images, the other will be programmed to record video. This is followed by an IR sensor, a thermistor array, a UV sensor. Next, we'll go over the first set of our requirements. These all have to do with power. The electronic section shall output 3.3 volts to the sensor and booster pack, as well as the Neo M&M GPS. Shall supply 5 volts to our primary microcontroller and 9 volts to our secondary microcontroller. Finally, each payload shall have a power system capable of powering it for more than 4 hours. The first set of our tests has to do with these voltages. The purpose of this was to make sure that the 5 volt and 3.3 volt regulators in the circuit boards were working correctly. The performance metrics were these voltages, and the testing method was to apply a multimeter across the power wires and across the voltage regulators. The results of this test were for each of the payloads, the regulators worked as expected. However, for the electronics bay, due to the fact that we were powering the MOSFET with the regulator, it drew far too much current and burned out the regulator. So that was not successful. And the 9 volt battery correctly supplied 9 volts to the redundant controller. Next, we have a battery life test. The purpose of this was to make sure that the battery would last the length of the test. And this was done through programming all the microcontrollers with IR embedded workbench, and we used a power indicator LED to figure out whether the payload was still powered. We plugged in the battery, we left, returned in 4 hours, and saw whether the power indicator LED was still on. The results of this test were after 4 hours, the power indicator LED was still on. However, at about 4.5 hours, this had turned off. Next, we'll pass it off to Christopher Cario, who will be talking about the next set of requirements and the next set of tests.
Thank you, John. As my colleague mentioned, my name is Christopher Ricario, and I'll be presenting more on the payload and electronic subsystem. So first, I'd like to go over our communication requirements for our subsystem. So our first requirement is that the electronics section shall output 1 amp of current to the parachute ejection system 4 seconds prior to apoapsis, and then again at apoapsis. Third requirement is that the electronics section shall output GPS data to the 3DR radio set at a rate of 9600 bits per second, and then shall output that GPS data on the 950 megahertz ISM band at that same rate to a distance greater than 1,000 meters. So first, I'd like to go over our accelerometer test. So our performance metric analyzed in this test was the acceleration. Our analysis methods and tools were putty.exe, which is a program that is used to convert UART serial input into ASCII characters. The IR embedded workbench, as John mentioned previously, and from these two, we've used the values gained to calculate the calibration constants. So our method of testing was to place a launch pad shown here with the sensor hub on each of its axes, and then using putty to record the measured values of each of those axes. Next is our gyroscope test performed on this turntable. So our performance metric analyzed in this test was the angular velocity. Similar to the test before, we used the same analysis methods and tools. And for this method of testing, we placed the launch pad with the sensor hub on each of its axes, rotate the turntable at a rate of 0.52 radians per second, and then using putty as before, record those measured values for each of those axes. Note that, as Jonathan mentioned before, there's a TI launch pad and sensor hub on each of the payloads. And given that there are 3 axes, we had to measure these tests 21 times. So to go over the results of these tests, the accelerometer and the sensor hub measured a gravitational acceleration between 9.2 and 9.9 meters per second, compared to the theoretical value of 9.77 meters per second measured here in Prescott, Arizona. The measured angular velocity for the gyroscopes were between 0.45 and 0.55 radians per second, compared to the table rotating at 0.52 radians per second. Next, I'd like to go over the chiller test. So the performance metric analyzed in this test was the data recorded. The methods and tools were the IR embedded workbench. And this equation here, data frequency, which equals to the amount of data gathered divided by the time measured in. So our method of testing was to turn on the launch pad and sensor hub, place in this temperature vacuum chamber, and cool to -7 degrees Fahrenheit. And upon that time, calculate the recorded frequency based on the amount of data gathered. Next would be the primary controller temperature test. So our performance metric analyzed in this test was the current measured. And so we use IR embedded workbench and the multimeter. And similar to the test before, we turn on the launch pad and sensor hub and placed it back into this temperature chamber, chilled to -7 degrees Fahrenheit, and then wait for the current to spike and measure that maximum current with the multimeter. Unfortunately, due to technical malfunctions with the temperature vacuum chamber, we were unable to perform these tests. Next is the primary pressure controller test. So our performance metric analyzed in this test was a current measure. We used the iron-embedded workbench as before and the multimeter. And so we turn on the launch pad and place it in the vacuum chamber, lower the pressure to 18.7 kilopascals, measure the maximum current with the multimeter, and verify that that was the maximum current measured. Next is the redundant pressure test. And so our performance metric analyzed in this test was current. We used a multimeter for our tools. And as similar to the previous test, we turn on the egg timer cork, which is our redundant flight computer, as John mentioned before. Place it into the vacuum chamber, lower the pressure to 18.7 kilopascals, measure the maximum current with the multimeter, and verify that that was the lowest maximum current at the lowest pressure. Our results of these tests were that the egg timer cork produced 0.55 amps of current when the vacuum chamber began to increase in pressure, and that the electronics bay produced 0.6 amps continuously, which failed to meet our requirement of outputting 1 amp 4 seconds prior to apoapsis. Next is the electronics bay launch test. So our performance metrics analyzed in this test were the deformation and cracks of the electronics bay structure, shown here. The IMU and GPS radio functionality. And so our analysis method was to compare this to our ANSYS model. And so we turn on the electronics bay, record the base values of the sensor hub on the TI launchpad, assemble and place back on the vibration table, apply the 18.3 G acceleration loading that we would see at launch for 10 milliseconds, record those values and compare those to the base values of the IMU recorded in the beginning, and use calipers to measure the deformation of the electronics bay structure. Unfortunately, when we turned on the electronics bay components, one of the voltage regulators was damaged on the circuit board, and we were therefore not able to finish this test. Lastly is the communications range test. And so our performance metric analyzed in this test was to note the distance traveled before signal loss, and our analysis method was to note the distance traveled when the signal was lost. And so our method of testing was to turn on the GPS and radio and verify a stable connection, start the car, and drive out and note the distance when the signal was lost. The results of this test were that the communications range was less than 1,000 meters, therefore not validating our requirement. Next, I'd like to hand it off to Clark Anderson, who will continue talking about payload and electronics.
Thank you, Chris. As you said, my name is Clark Anderson, and I'll be continuing to talk about the payload electronic subsystem test and results. First, the next set of requirements is that the legacy should provide more than one payload configuration. The payload section shall record images at a frequency greater than 1 Hz, and that record measured data at a frequency greater than 5 Hz, and that each of the payload structures should be able to withstand the expected force in the shock cord as a result of descent, which is expected to be 220 newtons. To validate the requirement of recording data at a frequency greater than 5 Hz, we would do the data storage test. Unfortunately, due to a bug in our data recording code, we were unable to perform this test. If we were to do this test, we would record data for a fixed amount of time and then divide the number of data points by that time in order to determine the data recording frequency. During our other tests, we did discover that we were collecting sensor data at a frequency of approximately 12 Hz, and we know that at the act of recording that data would not significantly decrease that frequency, however it would decrease that, but we should still be able to meet the 5 Hz requirement. Next is the camera frequency test. This was for validating that we could record images at a frequency greater than 1 Hz. For this test, we recorded approximately a 2-minute video on each of the cameras, and then used these two functions in MATLAB on that recorded video in order to determine the frame rate. We discovered that both cameras recorded images at a frequency greater than 30 Hz, which far exceeds our requirement. To validate the requirement of withstanding the tensile force in the shock cord, we did the structural descent test. We did one test on each of the structures: the electronics bay, the circular payload structure, and the octagonal payload structure. For this test, we set up each of the payloads on the shock cord as shown here, and we fixed the shock cord at one end and then applied loads to the other. 220 newtons, approximately 50 pounds. Unfortunately, on the day of the test, we only had 20-pound increments, and therefore we applied 60 pounds initially, and then we unloaded it and applied the 60 pounds again, and then the maximum load we had was 80 pounds, so we unloaded and loaded the 80 pounds. Before and after each loading, we used calipers to measure each of the critical dimensions of the payload structures, and we used the measurements before and after to determine if there was any permanent deformation. For each of these structures, we performed an ANSYS analysis, and while there was loading, we would expect this amount of deformation. For these models, we applied a fixed constraint to the base of the shock cord and a 220 Newton load to the top of the shock cord. Unfortunately, these models were not able to accurately represent the interface of the shock cord and the payload. This is the test. This is a picture of the test that was performed on the octagonal payload. Unfortunately, due to the team's lack of experience in manufacturing, the variation in all of the critical dimensions that we measured was far greater than any deformation that we would have been able to measure. For the cylindrical payload, we had very similar results. And then the electronics bay. We were able to experimentally validate each of the requirements that is listed here. Unfortunately, we were not able to validate experimentally these requirements, except for the first one, which was to provide 5 volts to the launch pad. Most of these requirements were not able to be validated as a result of that 1 voltage regulator being damaged during the first test, and then the bug in the data storage code. For future improvements, we'd like to replace the voltage regulator that was damaged and rebuild that circuit so that we can validate the requirements that damaged part prevented us from validating. And we'd like to replace the MOSFET high current switch that we use with an optocoupler so that we could separate the power system for the ejection charge and the launch pad in the electronics bay. We'd like to improve the antennas on the electronics bay and on the ground station so that we could validate the communication range requirement. And we'd like to replace these plexiglass triangular mounts that you can see here. Those are currently made out of 3 individual parts that are then welded together. We'd like to replace that whole piece with 3D printer parts to ease manufacturing. And then we'd also like to write more accurate requirements. As we've seen with the redundant controller, we did produce enough current, or we produced current at apoapsis as was expected, but we did not validate our requirement because we didn't produce enough to meet our requirement, but we were able to activate the ejection charge, which is the objective. With that, I'd like to pass it on to Josco Carrillo for the recovery subsystem.
Thank you, Clark. Like you said, my name is Jose Carrillo, and I am the recovery subsystem team lead. Also on the recovery subsystem is Leila Shams. Our requirement states that the parachute component of the recovery subsystem shall slope descent of legacy to a speed of less than 7.62 meters per second. This is a visual overview of our subsystem. We have the parachute directly underneath the nose cone and the ejection canister underneath the wadding, which protects the parachute from the ejection charge. And then we have additional wadding underneath the ejection canister. This additional wadding is because we had to drill a hole through the canister to get the shock cord to go through it. That way we don't lose it every time we launch. And we would like to protect the payloads which are underneath that. The performance metrics we analyzed were descent speed and opening force. We used MATLAB for all of our analysis. And we performed a quick leak tensile test, a shock cord tensile test, and a black powder and wadding test. For our descent speed analysis, we numerically integrated acceleration. This is a 1D analysis, and we found that a 10-foot diameter parachute gives us a descent speed of 5.5 meters per second. Using that descent speed, we also wanted to calculate the force on the shock cord. So we used this free body diagram, and we found that the force on the shock cord is equal to the drag force minus the weight of the rocket. For the drag force, we used CX, which is an opening force coefficient. This accounts for that initial yank from the opening force, and it's specific to the parachute canopy type. In our case, CX is 1.4. In addition to that, we also used the factor of safety of 1.4, and we found that the force that the shock cord and the system will experience is 93 newtons. For the quick link test, we tested, tensile tested these quick links. It's too small to fit into the loading frame, so we had to create testing grips that would loop through the quick link, so we can load it into the United load frame. As well as the shock cord, it's too thin to fit into the loading frame, so we actually folded the ends of it and epoxied them. That way it would fit into the clamps of the United load frame. Again, we wanted to see that they could withstand at least 93 newtons. The rating for the quick links were at 3,900 newtons. After we tested them, we found that they actually withstand 18,000 newtons. And the rating for the shock cord was at 10,000 newtons. After we tested it, we found that it only withstood 1,200 newtons. We believe that this discrepancy is due to the fact that the shock cord broke right below where we epoxied it. So we think the epoxy actually altered our results. However, both values still passed our test criteria of 93 newtons. In the future, we'd like to have more shock cord specimens to test. There was a miscommunication with the manufacturer when we asked for scraps of the material. They only sent us one, so we could only test one of them. We would also like to find a different way of loading it into the load frame. That way we can get a result that's closer to what the manufacturer is stating. We also want to test the connection between the quick link and the shock cord, as well as the connection between the quick link and the swivel link on the parachute. There will be higher stress concentrations there when the parachute opens, and we'd like to make sure that it can withstand at least 93 newtons. With that, I'll hand it over to Layla Shams, who will continue talking about the recovery subsystem.
Thank you, Hosta. As she said, my name is Layla Shams, and this is the continuation of the recovery subsystem. So the next test we will discuss is our black powder test. For this test, we utilized a test stand made of 1/4 inch thick steel, pictured here. Inside the test stand, you can see our aluminum ejection canister, both here and here. And inside the canister is our ejection charge. The load cell that we had used to record the force generated when we ignited the ejection charge is here, and this center figure shows our test stand with the load cell in place. The next test we did was the wadding test. This test utilized the same configuration as the black powder test, with the only difference being the addition of wadding in and around the ejection canister. We determined how much wadding we needed via visual inspection. That is to say, the furthest pieces of wadding from the ejection charge, if they were burned or singed after the test, that means that we needed to use more wadding. We sized our ejection charges using MATLAB. We found that a 1/2 gram ejection charge would be able to produce enough force to eject both the parachute and the nose cone. However, when we began experimenting, we found that this was not the case. We started increasing the sizes of our charges up to 4 grams. The 4-gram charge was able to eject both the parachute and the nose cone. However, the parachute wasn't able to be completely unraveled. Because of this discrepancy, we took a look at our MATLAB code and we found a few errors. Once we fixed those errors, we found that the optimal size for the ejection charge would be approximately 6.5 grams. For the wadding, we found that approximately 75 sheets or 1 package of Estes wadding, pictured here, would be enough to protect the parachute, the payloads, and the surrounding structure. We also determined during our tests that an aluminum plate, pictured here, or modeled here and pictured here would be helpful in building up the force to eject the parachute in the nose cone. We tested two configurations, once above the ejection canister and once below the ejection canister. We found that having the plate below the ejection canister actually produced the results that we had hoped for. So in the future, we would like to use a different data gathering method. The load cell is meant for static loading, and that is not the kind of load produced by an ejection charge. Not only that, the load cell it doesn't have a high enough frequency to actually record at the speed that the ejection charge produces the force. So we would also like to have a gram scale as well as materials to make the ejection charges on site at the time of the test. We continually found ourselves having to stop the tests and restart later in order to go and make more charges. But this was exceedingly inefficient to getting the work done. We would also like to be able to test the larger charges to reflect our modified MATLAB code. And finally, these are the tests that we performed. We have our shock core tensile test, our quick link tensile test, our black powder test, and our wadding test. Each of these tests were used to validate our descent rate requirement. The quick link and shock core tests numerically and experimentally validated our requirement. The black powder test numerically validated our requirement. However, because we weren't able to test the larger charges, we weren't able to experimentally validate the requirement. For the wadding test, we were able to experimentally validate the requirement. However, because there isn't an applicable model for wadding, there isn't an applicable numerical validation for this. And with that, I would like to hand it off to Sage Bauer for system integration.
Thank you, Layla. As she said, I'm Sage Bauer, and I'll be talking about the system integration. With me is David Gomez-Herrera, the assistant project manager, Andrew De La Rosa, and Kyle Hassel. So first I want to go over the system level requirements. First we have the apoapsis of the legacy's orbit shall be greater than 9,000 meters with respect to the launch pad. The apoapsis of the legacy's orbit shall be less than 9,000 meters with respect to the launch pad. Legacy shall transport 6 scientific payloads. Legacy's total payload mass shall be less than 10 kilograms. And the Legacy structure shall withstand more than one flight. Legacy shall use a motor with a fuel impulse less than 40,960 milliseconds. And finally, the launch pad shall point Legacy within 20 degrees of the vertical, and the launch pad location at launch shall be 1,500 feet or more away from any public highway on which traffic exceeds 10 vehicles per hour. So going over our performance metrics for those requirements, for our first two apoapsis requirements, we analyzed those using a custom MATLAB code and also the program OpenRocket, and we were not able to actually test these due to the flight test being canceled. For our two payload requirements, we analyzed these by modeling the payloads in CATIA and also applying appropriate densities to all the payload components and weighing the total mass. And we tested these both during the Legacy assembly test where we gathered about the payloads, weighed them, and also put them into the rocket. Next, for Legacy structure shall stand more than one flight. The performance metrics we analyzed here were the structural integrity of the rocket, as well as the parachute drag coefficient, which determines the descent speed of the rocket. We analyzed the structural integrity with ANSYS, all the analysis that the structures team did, and we analyzed the parachute drag coefficient with MATLAB and also the data sheets from the parachute manufacturer. We tested these, the structural integrity was tested by the structures team, and the parachute drag coefficient was tested during the parachute deployment test. Next, for the Legacy's motor requirement of total impulse, we analyzed this just by finding the specifications for that motor on thrustcurves.org. And we were planning on testing this after the flight test was canceled. However, the bunker on campus is not actually large enough for the motor that we were going to be testing, so that test was also canceled. And lastly, for the launch pad pointing angle, we analyzed this just by using the wind loading analysis in ANSYS. And we tested this also during the Legacy assembly test when the rocket was put into the launch pad. And lastly, for the launch pad location,
We analyzed this just by looking at our prospective launch site on Google Maps, making sure it wasn't near airways. And this also was not actually tested due to us not launching the rocket. So talking about the canceled flight test, we had planned that the flight test was going to validate all of those system requirements at once. However, as Michelle mentioned earlier, we had some problems getting into contact with the prefect of the launch site. And also, once we did, we found out that the Apoapsis deployment was not allowed at that launch site. And by that time, we could not find any feasible replacement launch sites for our rocket. So instead, the integration team came up with a few replacement tests. First, the legacy assembly test, where we assemble all the payloads and components into the rocket and the rocket into the launch pad. And also the parachute deployment test, where we make sure we can properly eject the parachute and inflate it and measure the drag coefficient. So going over some of the analysis for that flight test, you can see a model of our rocket with all of the forces on it, and also the equation that we numerically integrated in MATLAB, taking those all into account. And here you can see the results of our MATLAB code, and also the open rocket analysis, just the relative altitude. As you can see, the open rocket analysis is, relative altitude is much higher than our MATLAB code. We actually believe this is due to open rocket's relatively optimistic drag coefficients after Mach 1. And now I'll pass on to Andrew Del Rosa to talk about the open system process.
Thank you, Sage. As my colleague just mentioned, my name is Andrew Del Rosa, and today I'll be discussing the system test that the integration team performed to experimentally validate our system load requirements. I'll also discuss the validation status of those system load requirements according to the results from our tests. Also include a brief video showing the ejection charge portion of our parachute deployment test, as well as concluding with the future improvements to these tests. So the first system test that the integration team performed was a legacy assembly test. Its purpose was to experimentally validate the following three requirements: that legacy shall transport 6 payloads, the payload mass shall be less than 10 kilograms, and lastly, the launch pad pointing angle measurement shall be less than 20 degrees from the vertical. To numerically validate these requirements, we looked at CATIA models and an ANSYS 1 loading model for the launch pad. And then we split up the testing for the legacy assembly test into 3 different parts: the payload's accommodation, the payload subsystem mass measurement, and lastly, the launch pad pointing angle measurement. So for those numerical results, we looked at CATIA models, which had appropriate densities applied to all the components of the payload subsystem. We then used a measure inertia tool in CATIA to calculate the total weight, or excuse me, the total mass, which came up to be 2.577 kilograms. For the launch pad pointing angle measurement, we used a ANSYS model that would simulate the wind loading that the launch pad might experience on the launch site. And that maximum deflection angle was calculated out to be 0.1 degrees. Now moving on to experimental results for the legacy assembly test. The payload accommodation was successful. The integration team were able to physically fit all 6 scientific payloads into the upper structure without them getting snagged or getting caught in any minor imperfections of the structure. Seen here, you can see a setup photo before the test was performed. You can see the 6 stacked payloads right here. They are elevated using a few foam plates to simulate where they'd be sitting on top of the bulkhead, which is located right here. Now for the payload subsystem mass measurement test, we used a digital mass scale, placed a cardboard box on top of that scale, zeroed it, and then placed all the payload components in that cardboard box. We waited until the mass measurement on the digital display to stop fluctuating, and then record that measurement to be 1.701 kilograms. Now for the experimental result for the launch pad pointing angle measurement, we fully assembled the rocket and loaded it into the launch pad. We then moved all 8 guide rails, 4 on the bottom and 4 on the top, into their proper positions. We then used a digital inclinometer, which is a part of the Compass app on an iPhone, to measure the max deflection angle. We measured all 8 guide rails, and the one that showed the maximum angle, which was 1 degree, is shown in here in this picture and in that picture. Now for the second system test, which was the parachute deployment test, its purpose was to experimentally validate the requirement that legacy shall withstand more than one flight. To partially validate that requirement. The numerical validation for this requirement included looking at manufacturer data for the parachute drag coefficient, a MATLAB model that would compute the minimum drag coefficient required to still ensure mission success, and lastly, a MATLAB model for the black powder mass estimation. Again, we split this test into 2 different parts: the parachute ejection and the parachute inflation. So for our numerical results, we looked at the manufacturer data that was given to us from the manufacturer for the parachute. That drag coefficient was 1.23. We then used a MATLAB model to compute the minimum required drag coefficient to still ensure mission success, which came out to be 0.5. In that MATLAB code, we use this equation shown here, which is the acceleration of the acceleration of the rocket when it's descending in its flight with a fully inflated parachute. And here's a list of all the defined variables. For the MATLAB black powder model, pre-test, again, as the recovery subsystem team mentioned, it was 0.5 grams. Post-test, it was 6.5 grams. Again, this recalculation was necessary to account for the Nesman friction. Then moving on to experimental results. The calculated drag coefficient from the parachute inflation portion of this test was 0.46. We used the wind speed measurement from the anemometer and a spring scale to measure the opening force. Shown on the right is a picture when the parachute was fully inflated. Here at the top, our program manager, Michelle Machado, is taking a wind speed reading using an anemometer. And then down at the bottom, you can't see it, but there is a spring scale that is being attached to the bottom of the tether to take the opening force. It's worth noting that this measurement was taken with holding the spring scale. We realized that post-test that this is not the ideal method to measuring the opening force. However, we include at the very end of these slides a future improvement to this test to get a better result. For the black powder required, we started again at 1 gram, which was twice the estimation from the pre-test MATLAB code. We then added an aluminum plate into 2 different configurations with using 2 grams, as the recovery team mentioned earlier. We eventually incremented up to 4 grams, which was found to be the necessary amount to fully eject the parachute and the nose cone out of the upper structure. As seen here in this photo, with the parachute fully ejected out of the upper structure and the nose cone as well. Note that we used 3 different fans that had 3 different air speeds. Again, this was probably not an ideal case. However, that was the equipment that was available to us on campus. So the propulsion lab blower, the machine shop fan, and then a standing pedestal fan. For the black powder estimation, a higher mass is needed to fully ensure that the tethers or the cords on the parachute are fully unraveled to allow proper inflation when the parachute is ejected from the upper structure. You'll see later in a video that in this case, which is the 4 gram case, that the parachute cannot be fully unraveled. Now, a brief summarization of the validation status of our system load requirements. The 2 apoapse requirements cannot be tested due to cancellation of the flight. The requirement that Legacy shall transport 6 payloads was experimentally validated using the Legacy City test. For the requirement that the payload bay mass shall be less than 10 kilograms, again, this was experimentally validated using the Legacy City test. For the requirement that Legacy shall withstand more than 1 flight, this was not experimentally validated according to the calculated drag coefficient we found from the parachute inflation, which was 0.46, which was less than our minimum required that we calculated using our MATLAB code. The requirement that the total impulse shall be less than 40,960 Newton seconds cannot be tested due to the size of the bunker on campus being too small for our own motor. The requirement that the launch pad's pointing angle should be less than 20 degrees from the vertical was experimentally validated using the using the Legacy Ceiling test. And lastly, the requirement that the launch pad location shall be 457.2 meters or 1,500 feet away from any major highways was not tested because of the cancellation of the flight. Now, on the next slide is a brief video showing the parachute ejection test as well as the parachute inflation test. Now it's worth noting on the fifth test, for the ejection charge test, that all the fans were turned on to try and see if the parachute would inflate when the parachute was ejected from that perspective. Now moving on to a few future improvements. For the legacy assembly test, we would like to measure the mass of a fully assembled payload subsystem to reduce the chances of us forgetting any components in that measurement when we put all the components into the box. We would also like to measure the mass using multiple scales to reduce calibration errors. And lastly, take pointing angle measurements during the simulated mid-loading test that the Launchpad team conducted on our Launchpad to better compare our experimental results to the ANSYS when loading one. And lastly, for the legacy parachute deployment test, we would like to continue testing incrementally larger amounts of black powder to better compare that to the post-test estimation of 6.5 grams. We would securely fasten the spring scale to an anchored surface or object. Again, this refers to when our technician was holding the spring scale to take the opening force measurement. With this improvement, we would get rid entirely the human error when we're holding the spring scale. We'd like to take an anemometer reading from the edge of the parachute to obtain overall wind speed. We'd like to attach the anemometer at the end of the same pole to simplify the experiment and neglect the need of using a scissor lift. And lastly, repeat the test in a wind tunnel or with many identical fans to reduce turbulence experienced by the parachute, as it is obvious that there's a lot of turbulence seen with using 3 separate fans. And with that, I'd like to pass it out to David Gomez-Ferrer to talk about configuration management.
Thank you very much, Andrew. As my colleague mentioned, my name is David Gomez Herrera, and I'll be presenting configuration management. Excuse me. Configuration management is the set of documents that properly classify every part used for this system. You can see here we have our full assembly system. In order to understand this set of documents, we need to understand how they're made. Every document is clearly labeled by a 9-digit number divided into 3 different categories. The first category, called family, represents predefined classifiers by our Embry-Riddle documentation library. These are the families used for our project. The second set of numbers is an instance. These are individual projects identifiers, so it's easy to identify parts between different projects. Our main instance for this project is 0087, and our subassembly instances range from 0384 to 0439. Finally, the last set of numbers is called flavor. This is to classify parts that are very similar to each other. As we have here in our example for the spars used for our rocket, we have all these 4 spars are made out of the same material. They have the same thickness and the same width, although they have different lengths and different amount of holes. In this particular case, the flavors were assigned based on the shorter spar will receive a lower flavor for the first digit, and the second digit will represent the amount of holes on the spar. This is noted that it's different system for every part, how the flavors get assigned. Here we have our product structure tree, or part of our product structure tree, which represents how the system gets assembled together, starting on the lower levels, which have only individual parts, building up until we have our fully assembled system. For this case, this will be level 1, level 2, 3, 4, and on our following page we'll have 5th level, 6th, and 7th level. It's noted that we have 6 payloads, and as an example, we're only showing payload 2. The other 5 payloads will share a similar branch configuration. Here we have the product structure tree on its document format. This is how it actually looks. Here's some important information about it. The part name, which is a brief part description. The part number, clearly labeled here and here, as well as the page number on the document and current page, also labeled here and here. Also, we have a signature block, which represents the original draft of the document, the person responsible for that particular document, the project manager, and at the end, the person that authorized the release of the document. Every box represents a subassembly. Every subassembly consists of 2 documents, a 200-level document, which is a bill of materials, and a 300-level document, which is a subassembly drawing and instruction. Here we have an example of a 300-level document, which is for the launchpad. The first page will include an exploded view of the drawing. This drawing is exploded in such a way that it's easy to track where each component will go following the guidelines. Each part of that subassembly is clearly labeled by the part number and times that the part gets used. Again, in this document format with the respective information. Following pages to that document could be close-ups for smaller parts, so it's easy to track where each part would go. and assembly instructions showing how every part will go connected to each other. Some of these drawings, some of these documents which also include connectivity diagrams. These connectivity diagrams are mostly used for electronics, which represent, again, with pictures of each component where the cables will go connected between them. Here we have the 200 level document, the bill of material. Again, the example is for the launchpad. It includes every sub-assembly and part used in that particular sub-assembly, as we see, properly ordered by family and instance, first starting by all the sub-assemblies, and then going into individual parts. The flavors are shown right here, and then this number represents the amount of times that the part gets used on that particular sub-assembly. The individual parts, we have different types of templates. This will be for the most common one, which represents an individual part. It has overall and specific dimensions of it, as well as a tolerance table. The tolerances for this project were assigned depending on our machine's capability and also the manufacturing process that the part was going to follow. For flavor parts, we create what we call general templates, in which we mark the overall dimensions that are consistent between flavors, and then with letters, we specify which dimensions are going to change. Properly on another table, we identify the specific measurements and showing for which flavor they correspond to. For more general parts such as nuts, rivets, wires, or parts like that, we use what's called a universal template, which properly shows how to name the part, starting all the way from the instance. The last type of drawing part that we have are these, which are used for adhesives or pre-purchase parts. In this case, we'll include a picture of the part, and in case the overall dimensions are relevant, they'll be included. And as well, in a second page, application used to properly and safely use the part, or relevant information, like in case for electronics, there will be included voltage operation and a current draw. As a conclusion, our configuration management documents, which are these and these other binders, consist of 63 total sub-assemblies, in which we can find 128 instances breaking up into 58 different flavors, giving us a total of 186 unique parts, and the total of parts used, as shown in here, is 1,180. This is the current status of the document. All the following is having delivered, and we're currently working on the PDF version of it. I'd like to pass it to Project Manager Michelle Machado, who will conclude talking about money.
Thank you, David. In conclusion, I'll be discussing the management part of this project. Here's our project budget. As you can see, a total of $4,650. We were given a budget from Allsbrook College of Engineering, and also we got an Ignite grant. We've allocated our money for each subsystem, as you can see here. And here's what we actually spent this semester. As we discussed in the beginning, we did not launch, so we did not purchase a motor. As you can see here, that is why we are well under our budget. We were given a fictitious budget of $500,000. It's broken down to these following categories. Management is any work done by myself, the project manager, outside of class. Engineering is any technical or research done outside of class. Technical is any fabrication done to the project. Professional development is any class time we have, so typically per week we have 3 class days, 2 hours long each. Administrative is any work done outside of class pertaining to presentation and document. And finally, holidays, any work done on a school holiday. Here you can see 2 pie charts. One on the left is what we have done in prelim last semester, and this is what we've done in detailed design as of yesterday. And here's a total for each of the categories that I just discussed. Here's the total cost from last semester and the total hours, the total cost for this semester, and the total hours. Here is the grand total for both preliminary and detailed design semester, and the total labor costs. Here are the following milestones we've had since January of this beginning of the semester, all the way till our system validation review of today. In conclusion, we were not able to fully validate our system due to the following reasons of not being able to launch a rocket at the launch site with our design of our project, issues with parts breaking or the capabilities of our facilities on campus, and we've learned all lessons the past 2 semesters working in preliminary design and detail design. First of all, we have learned we need to properly communicate between subsystems. That is a huge issue that we need to learn, as you can see, with the big team we have here. Also, we have to plan for things to go wrong. As we discussed, a lot of things went wrong during our semester, so we have to allocate for additional time to test and also ordering extra parts in case anything breaks. And also, when creating the design and the preliminary design phase of our project, we have to consider the fabrication process. During detail design this semester, we realized that when we actually were in the machine shop, the design of the logistics of how we're going to make our parts were a lot more complicated than we expected. So when we actually, if we go back to the preliminary design phase, we would want to probably simplify this in order to not probably fall back behind schedule and losing more time when it comes to testing. We'd like to thank Dr. Benavides and Dr. McElwain for being our advisors for this project. And also, we would like to thank the following panelists for attending our presentation today. And also, as you can see here, are the following individuals and organizations that have contributed to this project. And at this time, I would like to invite up the rest of the team up for any questions.
Before we start with our question and answer session, Jody Davis, Oleg Sidney, Niall Little, myself, 12, 13 years ago, maybe I shouldn't say that big, but 12, 13 years ago, we were in our student shoes presenting our presentations for spacecraft detail design. And I'd like to introduce our course instructor for spacecraft detail design, Dr. Jim Lyle. I'll turn it over to the panel.
All right, good job. I'm thoroughly impressed. A couple things that actually impressed me. You guys conveying your numerical and experimental results very clearly for each subsystem, the testing that you went through. And I thought you were very thorough and you've accomplished a lot in terms of testing, fabrication, requirement verification. That's a lot of material to cover in what, an hour and a half? I mean, very impressive. I also thought you were all very professional. I'm glad that you indicated, Michelle, last thing, that communication should be a priority because that can be a major inhibitor in now and in industry. So I'm glad that you guys noted that. Before I started work on James Webb for hardware integration and test, I worked flight dynamics. In particular, the low density supersonic decelerator was a flight test program led out of JPL with NASA, and we launched out of Hawaii. And so I have, my background is largely, trajectory simulation. And I did note, in terms of the recovery section, I didn't see a specific requirement for parachute opening and load, unless I missed it. I think there was a descent speed requirement, but.
There wasn't. That actually should have probably been part of our future work, where we would like to add more requirements to the subsystem.
I think that's a great answer because, the concern there is you don't want to shred the parachute when you open it, and you're very sensitive to trajectory conditions, in particular Mach number and atmospheric density. So modeling that, you might want to go down a nominal path, but you really need to look at the dispersions in your atmosphere and vehicle performance to be able to characterize not just a nominal opening load, but something that is more of a worst case, so that you guys can stay under that depending on what you find in testing. So I did note that. And then what parachute was it that you guys were using? What manufacturer?
It was from Fruity Shoots. It was a 120 inch or foot diameter. No, inch. Sorry, inch. Yeah. Sorry. Annular parachute.
Okay. Okay. That would be good just to list that out. What that is. Let's see. Oh, another very important part with recovery is landing footprint. So with LDST, when we were out in Hawaii, we were landing in the ocean, but we needed to recover that because we had data on board that we had to recover in a timely manner. So in terms of landing footprint, a footprint that you have that includes dispersions in atmosphere, aero, knowing that so that you can really adhere to any safety issues. I don't know exactly the location that you're launching, but recovery would be very important with that. I'm not saying a full-blown Monte Carlo analysis or anything like that, but develop some worst-case trajectories. And then the other comment I have, well, just a question with the shake test on slide 67 that was performed. I don't know if I heard right, a manual shake test, or were you guys actually on a shaker table?
Yeah, you heard correctly. That was a manual shake test that was conducted. It was a very simple test just to verify that all the parts were firmly in their place. During that test, we actually did discover that one of the spars in the payload section had become loose, and we fixed that and performed the test again, and then the requirement was validated.
Okay. The only thing I would encourage there, and I know facility limitations are, come into play, but fully assembled 5 tests would be ideal. But I know you guys are kind of constrained. Let's see. Oh, and then the other comment I had, ensuring that you adhere to hardware management when you guys are kitting everything up for your final integration. It's so important because you're trying to adhere to schedule. So making sure that you have everything kitted up, fasteners, washers, all the small pieces so that you're not running around trying to gather things when you're assembling for the last time. So that's important, and I thought you guys had a good handle on configuration management. That was very impressive. And then how much does the motor cost? I missed that.
$1,800.
$1,800.
And that was without the motor casing. So we just purchased the motor casing so we can fully assemble everything like hardware-wise.
Okay, so without the motor, you were at like 2,200 or something like that. Okay. I think that's it. I'm very impressed. You students have come a long way. You guys are just doing a really good job, especially for such a big group.
I have a few comments. But in general, I want to say the presentation was very well done. Really good organization, the way you present the briefing is outstanding. I will caution you that, and it's a common problem when you're have a time limit, is you sometimes tend to speak a little fast. So watch your speed when you're speaking in a forum like this. The faster you go, the harder it is to understand you. So that's something you ought to watch. I have a few comments and questions. With respect to the range, that's something that you probably should put in as a lessons learned to negotiate right up front before you start your design. Because obviously, the range is telling you that your design is not flyable there. And so you're going to essentially have to either redesign your trajectory or find another range. And so I think that's a great lesson learned for you to say, hey, we need to make sure we understand what our requirements are going to be from all of the ranges and all of the exterior environments that we're going to be in, and make sure that those are in before you start your actual design. I don't have my computer manifested like you. That was quite good. When you did the heat test, gun test on the composite, one of the things that you did was you tested it one time. This is going to be a multiple use rocket, so you almost, and this is a comment that can apply to anything on the vehicle that might get thermal stressed, like composite sections. So when you're trying to design something that's for longevity and multiple tests, it might have been worthwhile if you could have done some kind of thermal cycling on those pieces that you have thermal concerns for. Composite sections sometimes can crack and or have stress problems during thermal cycling, and so maybe after the first test it would have been fine, but if you did 5 thermal cycles, you might have found that something might have been damaged on it. So that's something that when you're looking for longevity, for one-time use, that's fine, but for longevity, you have to think about how many different cycles of either thermal or pressure or whatever that it's going to go through.
Thank you. Kyle, could you go to slide 224? That seems to be the incorrect slide. Oh, 244, sorry. Thank you. So we did realize that our thermal test was a bit inadequate. So we had designed this to hopefully perform it in the future. We didn't actually consider going through multiple tests to determine the thermal cycling, as you suggested. That's a very good idea, thank you. But we did realize that our nose cone would be under loading, and during our test we didn't have a way to put the nose cone under the load that would be experiencing by the dynamic pressure. So we were hoping to conduct this test shown here at some point in the future, but due to time constraints we were unable to get to it.
Well, one of the things that industry likes to say is they like you to test as you fly. And so, given that you were going to go through a number of different cycles, it would have been worthwhile for you to look ahead and say, okay, what types of testing can I do? And you know, in industry, at system level testing, you do thermal cycle, you do thermal vacuum, you do vibration, and you do multiple tests, multiple cycles of those things where it's appropriate to do that. So that's just one of the kind of things that you'll learn as you get into industry. On page 58, on chart 58, where you talk about the carbon fiber proof testing that you did, that was not on the unit that you actually flew, is that correct? That was a
That's correct. That was it on a test question.
So for at least the programs that I'm involved with, anything that is made of carbon fiber or composites or anything like that, since there's virtually no way, unless you can do some kind of non-destructive testing on an ultrasound or something like that, to verify that it's manufactured properly, that there aren't cracks or imperfections in the manufacturing process. Most of those kinds of things are each flight unit is proof tested. So that's something that you may find useful in the future.
Kyle, could you go to slide 243? Yeah, so we did have a full structure compression test planned. Unfortunately, it was unable to be conducted because the facilities we have here did not include a load frame that was large enough to test either the full structure or the motor section or the payload section individually. But that is a test that we would have liked to conduct at some point in the future.
That would have probably satisfied the requirement. Most of these, I had a lot of questions about your test results, which you kind of all summarized at the end. I guess what I'd like to say about that is you probably learned way more on this project by having all of those problems than if it would have gone perfectly smooth all the way through. One of the things certainly is that when industry does something like this, they don't have the same kind of time constraint exactly that you have, where you are done at the end of the semester and you can't extend the project, but they will go through, and just as you talked about, they will add margins to their schedule where they can try and accommodate when they have problems during testing or build or manufacture or whatever it is. So that's clearly one of the things I think you learned out of this. But I really think that you benefited greatly from having all the failures. That's really where you learn. You don't learn by doing everything right. You learn by failures. So overall, I think the test program that you went through was really outstanding. The fact that you did so much testing was really a benefit. It certainly highlighted all the problems that you had and all the issues that you had. And so that's why test programs are immensely valuable, and you'll find that the more expensive the programs are, the more they tend to test. And they will make sure that everything is tested to the highest level they possibly can to give it the optimum opportunity for it to be successful on orbit. So that's really a good part of what you've done here. And I think that's about it. The big management section was outstanding, just like you had said. That's something that the industry sometimes doesn't do all that well. You guys do a great job of that here. So overall, you guys did a really nice job.
Thank you very much.
Okay, so I've got a few questions and just some comments. Slide 52, where you're outlining the numerical versus experimental mass. I'd like to have just seen the experimental numbers, just because you showed there is a difference between both experimental and numerical methods, just to see what the comparison was. My next question was for the rivet drill out test on slide 57. Now, I believe you all said that this was designed to show that the fins could be replaced if necessary, but then you also said that this test itself can only be conducted once because the act of drilling out a rivet changed the actual configuration of a fastener system. Would that not inherently then prevent you from putting a new rivet in to swap out a fin?
All right, that was slightly misstated. The test can be conducted multiple times, of course. The issue is that we found that you had to step up the drill bit one size to successfully drill out the rivet. However, if you take a size 41 drill bit, drill a hole through the pieces of metal and insert the fin, use a rivet gun to put a rivet into the hole and secure it in place, and then take a size 42 drill bit and drill out the rivet that has been inserted. It may be successfully drilled out, and a new rivet may be inserted into the new hole and clamped into place securely. So with no problems, because the difference in the hole diameters is very small and the rivet is still very firm. However, if you try and drill it out a second time, the rivet will spin in place, and that was the problem we were encountering. And for that reason, we can only replace each of our fins once.
Okay. That was the concern I had, was the multiple use and replaceability of those fins. The next question I have is slide 67, kind of a shaker test. Was any test ever designed or conducted that would have basically run the same experiment but with the payloads actually inserted within the payload section to see how they would behave in an all-up system?
No, I don't believe any test was conducted specifically to include the payloads.
Okay, that would be something I would recommend in the future.
I should mention, though, that we did have a payload accommodation test, which I believe was discussed. And that was just to verify that the payloads did fit securely inside of the payload section.
I understand that, and it's one thing to show that they fit, but it's another thing to show how they'll react to the vibration environment within that section.
Thank you.
And then I think the last question I had was regarding the ejection charge tests on slide 136. And you mentioned that there was an error in the prediction code. That's why you thought that there was a smaller amount of powder needed for the charge. And then you eventually went and found that there was this error and fixed it and found the actual optimal charge size at maybe 6.5 grams or so. Why was and you mentioned that you would like to conduct a larger powder charge test, but why was one itself not conducted?
For multiple reasons, we weren't able to conduct a larger test, a larger charge size. The main one being time constraints. We honestly ran out of time. We couldn't, based on the time. Also, safety had qualms with us getting any bigger than, honestly, 2 grams. So,
testing in an enclosed building, I can understand. All right, thank you. That was all my questions.
All right, try to be a little more organized this time. So, could you go to slide 21? So my first question is, do you guys have any justification for why your experimental yield stresses for aluminum were so much smaller than the published yield stresses? Did you look into that at all?
I'm sorry, can you please repeat the question?
Oh, I'm looking at this table, I noticed that your aluminum experimental yield stress testing yielded about half of the published yield stress. Did you guys look into those, or did you?
Yes, so there were, yes, there were some issues with fabrication and the actual test itself. The biggest one being, when we did do the tension test, the bottom grip clamp, the spring was a little loose, therefore it wasn't fully secured on the bottom. We had to hold it to 100 pounds of force, and then we could let go. And it was also noticed that they did fail towards the grip clamps because of this, and also due to the heat treatment and strain hardening from the fabrication. So.
Okay, just following up, so if you looked into it. Slide 51. I noticed, I guess I'm a little bit confused to your mass requirements. Slide 51 shows as a pass-fail criteria that the total mass is to be less than 4.5 kilograms. And on slide 150, it said that the payload mass alone must be less than 10 kilograms. So your total mass is less than 4.5, but your payload is.
Yes, this, I'm sorry, can you go back to the slide instructions? This is referring only to the mass of the structure, which does not include the scientific payloads or the structure.
Was there a total mass that I missed somewhere?
No, it's just the
It was broken out. Okay, so I was just confused because there was no total mass requirement.
Correct. We were just given a max.
So we did calculate the total mass, just in comparison with the current mass, with the previous mass budget we developed in prelim design. We have the breakdown of it. I guess we didn't add all of them.
Is this a backup slide?
Huh?
Is
Yes,
this
a backup slide, yes. Yes, we didn't present that part, although we don't have all the mass because we didn't purchase the motor. So that couldn't be included. Also, the motor casing arrived after we conducted this test, which is the reason why it's also not included here.
Okay. So you guys were never given specific weight or mass and size restrictions for the payloads?
Not for the total. For the payloads, it was given 10 kilograms, but not as a total system. Payloads specific.
Okay. Okay, that clears that up. And then I just wanted to also, I mean, you mentioned a lot of things, but the importance of cycle testing your components and everything, especially when you're trying to validate a requirement of a multi-mission or launch requirement, or to satisfy that. And just a couple comments. You guys did a great job, by the way. I'm really impressed. Just a few little comments on the presentation. I would have liked, because there were so many tests that were done, and we have to do them really quickly, I would have liked to see requirements shown, or I'm sorry, results shown kind of for each test on that slide. Sometimes I think once we got into slides 97 and a little bit past that, I started to see that the results were summarized like 3 slides later, and I was like, what test is that, and what were the, seeing it all on one slide I think would be really beneficial. And then, let's see, can you go to slide 130? So, question with this test, are there loops on the ends of the shock cord that the quick link actually connects through for the actual setup?
I can actually show you that. The shock cord comes with loops pre-sewn.
Okay.
So that's here, you can see that here.
Yeah.
As well as on the other end connected to the motor casing. However, the piece of shock cord that we received to test
Was not sewn?
was not sewn.
Oh, okay,
Which
so
is
that
why
makes it
we had
difficult.
to epoxy it.
Okay. So you epoxied it and you clamped the whole thing
Yes.
here? I see, so you just had to deal with what you had on that, okay. Whereas an ideal test might have been to actually test it with some kind of loop to see if there's any, if you have any failures in the loop itself.
Exactly, and
Okay.
we should have put that up there. We should have tested the way you suggest, but we only have
Yeah,
one piece.
yeah, you're restricted to what you can do. Let's see. I think that's pretty much everything I had. One comment on the, I can't remember what slide slide it was, but the configuration management, yeah, the connectivity diagram. Do you guys, was it a time constraint that you didn't put together a wiring diagram or something a little more technical at the table?
So on the configuration management document, there's included as part of the assembly of the individual parts for the circuit boards. There's included schematics of how they go and also board diagrams. For these ones, there's also included a schematic, but it's more like a physical representation of which cable will go connected to each terminal.
But there is information.
Yes, there is
on how those
information.
connections are made more specifically. Okay.
Yeah.
Great. Just looking at this, I don't know if I can put all that together and kind of do the reaction. I commend you guys did a really great job. This is really cool project. I wish you could launch it. That would be great.
I want to echo what the other panelists have said, how much you guys have achieved in the amount of time and shapes that you guys had. It's really impressive. I also want to say that I really appreciate that you guys select to use a dynamic cloud computer. That's pretty much standard industry practice in aerospace, no matter the system. It's just so that's I really think that it's great that you guys do that and have the considerations of what was required to do to have to come to computers. I also want to say that things happen in the industry all the time. I myself, I'm sure many times have been on projects where you put your heart and soul into it, and then you watch the launch vehicle explode, and your payload is lost, and you pack up and you go home. That's it. So it's just that's actually the way sometimes things work. So you guys kind of gain that lesson here. But trust me, it'll happen again, and it's not how hard you fall; it's how you get up. So remember that. I do want to reiterate there's some many instances of violation of the test as you fly principle. Pretty much, if you violate if the test does not match how you're going to fly, you can't validate. You can't say it's validated. Well, with this assumption or this asterisk, it's pretty much the test is invalidated. So I want you guys to really, really take that to home. And nobody will let you fly a system that you can't show that you tested it, especially if you make special considerations. So you have to redo those tests. You have to change the test configurations. So speaking of that, I did have a question. If you guys were able to secure the launch that you had intended, how were the wires were actually going to keep the system in place and connect to the ground? Was it put stakes in the sand? Was there
Yes, it was just hammer the ground stake.
When you guys actually go out there, was that going to be even feasible? Because some sand is pretty loose, so.
The dirt around here in this area and Aguila, which is where our launch site was, is capable of putting the stake in the ground.
Okay. All right. And was there a reason that you guys couldn't do that test outside here and putting it to the ground here? Is that a safety issue?
For the wind loading test specifically, it was so no external wind forces were on the load. We wanted a controlled environment, so we can just see purely how those particular effects of how we loaded the structure affected it. That was one of the main reasons we didn't do that outside.
What about the pressure loading? What would you have done that one outside as well and had extra sticks in?
Yes, we could have, but we weren't sure. We did not conduct the test that way.
All right, fair enough. Oh, by the way, Excel is not an acceptable analysis tool, period. That whatever analysis was done through Excel, the test was going to be bought. And the reason is you can't run a validation script on Excel. So it's really easy to make mistakes. They've been made huge mistakes in industry. I mean, I think you actually see this in the business side more, where people use Excel sheets as their accounting tool, and you find irregularities and laws are broken. And so it's just it's an easy tool. We all use it, and it's a good first order. If you need to have a rough estimate. But then you have to put it into something that is code and something you can deliver somebody so they can verify, validate, and it's much easier to debug and find where those errors are. So just as an FYI, so first, NAT can kind of test that. You can't use that as an official verification test. So I want you guys to really, really take that to heart because so many mistakes have been happening and so it's an avoidable thing. I had a question on configuration management. Is there a way that you guys have easy to distinguish between flight and test components?
For configuration management, we didn't include any test components. All of them are the flight ones.
Okay. And then also, how did you guys label the system? You had so many parts that are many instances. In the actual assembly and tracking, how did you guys actually level each part so you know where it went so you didn't get confused with another part?
So mostly there's a predefined library where all the labels get added depending on the family, starting by the family, depending if it's a hardware fastener, if it's what type of part. So in there, that's where we assign them. Then on our CATIA drawings, we put the part of our name and then next the label, so we could correlate where they go.
I guess my question is, how did you guys physically label and track that, the actual parts? So,
On the assembly?
yes, the actual parts that I'm looking at right now, how would you guys be able to distinguish between bolt number 1 and number 7 if you needed to?
For which? The parts in there are not physically labeled. According to the management, we just know the part by its dimensions and the shape.
These are just the assemblies.
Okay.
They're all laid out in drawings.
Okay. Units. So actually, this has been actually a cause of many errors in the industry. I actually understand why you guys would present SI and English side by side, but because when you convert, so it's not always clear which one was the official certificate. So by presenting the units side by side with different metric systems, you're actually introducing two sources of truth. So if I was milling that part for you, I wouldn't know which is the official one. And I think sometimes the official one was the English, like 1,500 feet requirement. Actually, I think that's the value that was the official requirement, and you convert to metric. So that's actually pretty dangerous industry because once you convert, the significant digits don't transfer the same way if you do the conversion between the two. So actually, for the presentation, that might be okay, but if you ever deliver a drawing or actually something, never ever do you include two units in the same. So you just say, you pick one, and sometimes like the propulsion, you say DSI because that's how it works. And you just say that, you don't convert it into the metric system. So that's, so I appreciate that you guys put it in the presentation because it's sometimes easier to understand, but it does, in the actual manufacturing and verification, that will cause a lot of problems.
So in our configuration management, we have use metric.
Okay.
We have only one.
Good, good. So I just want to, and then my last big question was, what are the forward plans? Obviously, there's still a lot of work that can be done. Are there forward plans to wrap up some of these tests or the next team to come in and make some improvements?
Our plan is hopefully that another team will pick this up and improve our project.
We were also looking at actually continuing this class with a few of us who aren't graduating this semester. However, the hope was that we'd have someone from the electronic subsystem, and congratulations to all of them, but none of them are staying. So unfortunately, we ourselves can't do it unless we find another way around that.
Okay, fair enough.
All right. So everyone's gotten the easy comments and questions out of the way. But you guys did a truly amazing job. I really enjoyed it. And I had a couple things that I just wanted to ask you about for the ground system. I didn't see any failure analysis for like the L brackets or bolts or anything like that. Was that done? Or did you just sort of take into account the main structure?
We looked at the main components.
Okay.
The L brackets were considerably thicker. We do not perform an analysis of this. We do not have numerical values to tell you, but they were considerably stronger than the rest of our parts.
Okay. And payload, I love the modular payloads, and I thought you guys were very ambitious with having 6 separate payloads and electronics. That was outstanding. I loved it. One thing that I noticed, you do have dual firing, I guess, computers or flight control computers, and I like the fact that they were dissimilar too, so that if there's something that only affects one type of computer, you have your backup. That's different. One thing that I will caution about is, do you have any control system there to make sure that is one the primary, one's the backup? What happens if they're disagreeing? Who has priority?
The primary is designed to fire 4 seconds before apoapsis, and then the redundant is designed to fire at apoapsis. They use completely different sensors for triggering that.
Okay. And is there any fail-safe to make sure that they don't fire like while your rocket is still firing, or
yes,
right upon launch?
There are builds and things to the code for the primary controller to make sure that that doesn't happen. And the redundant controller is not programmed by us, but it has not activated prior to apoapsis in any of our testing.
Okay. Another thing that I noticed is, so the electronic subsystem failed to produce like 1 amp, or sustain 1 amp, but then it was mentioned that it was still able to perform basically what it needed to do to activate the nose cone and the parachute. So what was driving that 1 amp requirement?
That was the nominal amperage requirement for the ejection charge, but not the minimum.
Okay.
So the redundant controller met the minimum.
All right, so could you have changed the requirement, or is there anything in place where you can go back and say, okay, this is what we would like, but we're not able to meet it. Let's get someone to sign off on this and say,
yes,
we
probably could have changed that requirement.
Okay. Another thing that I noticed, sort of going along with some of the other comments, is I noticed like the inclinometer that was used was just like what, an iPhone level or something. You have to make sure that when you're doing testing that all of your test equipment is calibrated, and otherwise you can't really trust the results. I mean, his phone might say that it's 3 degrees, and mine might say that it's 0, like dead on, and someone else's might say something. So just be careful on the test equipment you use. It's actually really expensive, and these companies pay a lot of money to have all the equipment shipped out into a lab and tested and certified, and you have to do it very frequently. So another thing, configuration management, outstanding job. It looked great. That's sort of my background. So I enjoyed, like, you have a great product lifecycle management with your product structure trees, your drawing trees, and the bill of materials. One thing that I don't see more is how are the requirements managed? Because a lot of times the requirements management is a huge part of any project, and I see requirements scattered through here, but I don't see anything like where you have requirements documents that are managed and you have sort of change control over these documents.
So at least those type of requirements, they are included on our configuration management. However, that deliverable we haven't prepared. We're waiting to finish with this presentation to include all of our documents into it. But it is classified also in there. On the families, there are specific families for each type of document to be able to keep track of those. However, there's not a way to, or we didn't plan into adding those into a prog structure tree or anything like that in order to do it.
Yeah, that's fine. Sometimes it's like in a separate area, but it's still going to be controlled by configuration management and a process. So, but overall, excellent job. You guys did fantastic work, and you deserve a lot of congratulations.
Thank you.
I would like to thank you all. Thank you to the panel for coming in today, taking their time out to come in and ask us questions. We'll be standing next to our posters for the remainder of the afternoon, so if you'd like to talk to us more and ask us some more questions, please come and visit us. Yes, sir.
I just have one question. How many change orders were executed doing that? Approximate. Approximate number?
Over 100. Over. Thank you so much.